Yeah. All right, first little disclaimer, I have no idea how much you people know about the background info for this. So if at any point you have any questions, please just raise your hand like immediately. And I would love to answer them. If things are too easy, also let me know. I don't know, just either way. Yeah. All right. So today I'm going to be talking about me when I can't pronounce his name. All right, Eulerian circuits. And at the end, we're going to get to a quantum algorithm for them. And the idea is just kind of to give you a bit of background and also some motivation for why quantum algorithms could be cool if quantum computing ever advances further. All right, so outline, we're going to do a quick review of graph definitions. Then we're going to do a quantum computing speedrun, some background info on quantum algorithms, and then get to the core of the presentation. All right, once again, I did keep the slide for anyone who's not already in the Discord. Yeah. All right. So as people who were here last week will recall, a graph G consists of a set of vertices, and we're going to say that we have n vertices in our graph, and there's going to be edges between pairs of vertices. We're going to say we have n edges, so this is a graph. All right, so if we have two vertices that have an edge between them, they are called adjacent, or they're called neighbors. The degree of a vertex is going to be the number of edges with v as an endpoint, or otherwise the number of vertices that are adjacent to v. So you might see this denoted as d of v. We will not really be working with directed graphs today, but for future reference, the out degree is going to be the number of edges coming out of v, while the in degree is going to be the number of edges coming into v. So importantly, a cycle is a sequence of vertices, v1 to vk, then back to v1, such that every pair of vertices that are next to each other in the cycle are connected with an edge. And also, of course, vk has to be connected back to v1. So since we have k vertices here, such a cycle would be called a k cycle. So in this graph here, ACBD is a 4 cycle. So how are we actually going to represent graphs mathematically or in an algorithm? Say we don't want to draw a picture, we don't really want to bother with connecting a bunch of nodes to each other, we want a simple representation. So there are two main ways to do this. One of them is by using an adjacency matrix. So if we have n vertices, we're going to have an n by n matrix that's going to be full of zeros for the most part, where, well, depending on the graph, but you're going to have a 1 in any spot where vertex I connects to vertex j. And then you're going to have 0 otherwise. We can also have adjacency lists where we're going to be given the degrees of each vertex, and you'd also be given an array for each vertex v, which is going to represent all of the neighbors of v. So basically, you're going to be able to look at each vertex and be like, what other vertices is it connected to? So I guess we're gonna. How familiar are you all with adjacency matrices and lists? Like, would you like to go over it? Yes. Okay. Let's do an example then on the whiteboard, because I didn't feel like typing out the entire matrix in the presentation. So I guess we'll start with the matrix. Can people see here? I will try to draw large. All right, so we're going to write A, B, C, D, E, F. And so we're going to go vertex by vertex and just write down when it's connected and when it's not. So because this is an undirected graph, you'll notice that the matrix will actually end up being symmetric in the sense that you could flip it over the diagonal and it'll be the same. So what you would do, you look at A. A is not connected to itself because we're not allowing loops today. A is not connected to B either, but it is connected to C and D, but not E or F. Yeah, so once again, A is not connected to B is not connected to itself. It is connected to C and D and also E, but not to F. Wait, can people see this? Yes, okay. So then we're gonna look at C, which is connected to A, B, and also F. Here are the graphs. D is connected to A, F, and B. E is only connected to B. And then F is going to be connected to C and D. So something that you might notice about this is if you take the column for F, it's going to, and you like sum it all up, it's also going to represent the degree of that vertex, because F has two neighbors. Does this make sense? All right, so then we'll do an adjacency list. Basically, we're just gonna write down all the vertices again. And then go through and be like, oh, what are the neighbors directly? So for A, right, C and D. This would typically be in an array or list. For B, we have C, D, and E. And D, we're gonna have A, B, and F. So you're gonna end up with something that looks like this. And generally when you're coding this up, or at least for the purposes of today, we're also gonna say that you're actually gonna just be given the degrees of each one of these. So like you're also gonna be given 2, 3, 3, 3, 1, 2. So yeah, that's the idea behind adjacency matrices and adjacency lists. And we want to like just keep yes.
Oh, sorry. Because it's a like symmetric matrix, do the like eigenvectors tell us anything, or eigenvalues or eigenvectors tell us anything?
Okay, so there are parts of graph theory that can be like solved / simplified using weird linear algebra techniques, but I do not know them off the top of my head. Graph theory class. But yeah, and adjacency matrices are often used to like figure things out like this, but not for the purposes of today. All right. So, Eulerian circuits or Eulerian tours are closed walks, which is basically a cycle, but you can like repeat vertices that uses every edge in your graph exactly once. So I have a graph that contains one of these is going to be called a Eulerian graph. The graph I had before was not, so I had to make a new graph, but it's kind of hard to see here. But if you follow from A to D to E to B back to A, and then to E to C to F back to A, that is a Eulerian tour. Yeah, and they're pretty cool. So, interesting problem in graph theory is given a graph G, determine if it has a Eulerian circuit. So we learned last week about Hamiltonian cycles and that like finding / determining if a graph has them is NP hard. It is so much easier for Eulerian circuits because of this amazing theorem. And you'll notice that this guy has like 30 theorems named after him. So yeah. We're going to assume for now that the graphs we're working with are connected and undirected. A connected undirected graph has a Eulerian circuit if and only if every vertex has even degree. So meaning that every vertex is connected to an even amount of other vertices. So we're gonna prove this now. So let's say we're working with this graph, we have n vertices and m edges. And we're gonna say, okay, assume G has a Eulerian circuit. So, we're gonna go from V1 to V2 through so on. The vertices may and probably will repeat, but the edges may not. So we'll note that since we have m edges total, we're gonna go around. If we list all the vertices this way, we're gonna have m vertices. So we'll also, as we noted, the degree of a vertex is equal to the number of edges connected to it. So if we go through every single edge in our graph and we add, and we increment the value for the degree for the vertex on one side as well as the vertex to the other side, we can then find the degrees of all the vertices in our graph. So if we in fact do that, you'll notice that each time we encounter a vertex, we're encountering exactly two adjacent edges to it, which must all be unique because it's a Eulerian circuit. So since you are doing this, if you count up the degrees of the vertices in this way, you end up with all of them being even. Yeah. Then the other direction is significantly more annoying, but basically, so far we've proved if a graph G has a Eulerian circuit, every vertex in G has even degree. Yes.
Can you re-explain the second last point?
Each time we encounter a vertex one, yeah. So if we're going through this Eulerian circuit, and we look at a vertex, say we have a vertex A that appears at V2 and then a V5, for example. Each time we're going to encounter A, we're gonna have the edge to the left and the edge to the right. And so we have to add both of those edges for the degree. Does that make sense?
Yes.
Okay. All right. So other direction, assume now that we have a graph G where all vertices have even degree. How many of you have done induction before? There's a lot of freshmen. I don't know if all right, who hasn't done induction? Okay, awesome. You get to learn induction early. Basically the idea is that you're gonna say, it's kind of like climbing up a ladder. You're gonna basically be let's assume that the statement that we're trying to prove is true for n vertices, or for any graph that has less or equal to n vertices, and then you're gonna prove it for n plus 1 vertices, for example. Yeah, you'll see. I guess so we're gonna induct on the number of vertices n. We're gonna note that a graph with one vertex and plus 0 edges, because we're not allowed to loop, has a Eulerian circuit because there are no edges, so it just automatically has one. So now we're going to assume that every graph that has k vertices, where k is less than the number of vertices that our graph G has, we're going to assume that every graph like that with even degree has a Eulerian circuit. So we have n vertices in our graph G. We're going to choose some arbitrary vertex V naught, and we're going to remove it and its adjacent edges to create a new graph G prime. So we note that because every vertex of G has even degree, V naught must have had an even amount of edges. So we've removed an even amount of edges. We're going to say we removed 2x edges to an even amount of other vertices. We're going to split these vertices into pairs. For each pair, if they were already connected with an edge, we're going to now remove that edge. If they were not already connected, we're going to add that edge. So now each of the affected vertices in G prime, in terms of their degree, when we removed adjacent edges to them, has either lost one edge from V naught and then gained an edge, or it has lost 2 edges, which means that all the vertices in G prime still have even degree. Is everyone good up to this point?
No, let me go over the last two.
Okay, I can slow down if that'd be better. And if there's any specific questions, let me know. Yes.
For splitting the vertices into X pairs, can you have repeats of vertices within multiple pairs?
No. So we're saying that when we removed V naught and its adjacent edges, we removed edges to exactly 2x vertices because we removed 2x edges. And we're going to split them into X pairs. If we just put all our vertices in order V1 to V2x, we're just going to say V1 and V2 go together, V3 and V4 go together, and so on. So we should not have any repeats. All right. So, connected components, we did go over them last time, but in case, for whoever wasn't there, a connected component of a graph is going to be a piece of a graph where you can get from any vertex in it to any other vertex in that same connected component. So, now G prime has some number of connected components, each containing only vertices of even degree. By the inductive hypothesis, since each of these connected components must have less than, sorry, yes.
I think I missed something, but, why do all the vertices have to have even degree? Like-
So we assumed that G has even degree,
Yeah,
and then when we're constructing G prime, so we removed V naught, right? We removed an even amount of edges. We removed one edge to V1, one edge to V2, so on. For each of these vertices that we removed edges to, we either removed another edge or we added an edge. So each vertex is either back at the same degree or now has -2 degree. So if it had even degree before, it still has even degree now. Does that make sense?
thanks.
Okay. By the inductive hypothesis, each of these connected components must have a Eulerian circuit. Then we're going to basically go back to G and try to reconstruct a Eulerian circuit there from the Eulerian circuits of G prime. So for each pair of vertices that we that previously did not have an edge, but then we added an edge. If we now remove that edge that we added and add V naught back with its adjacent edges, we can go from V2I minus 1 to V naught to V2I instead of what we were doing before, which was going directly from V2I minus 1 to V2I. And similarly, the pairs of vertices we disconnected, we can re-add the edge and we can just kind of reconnect V naught into it to make sure that we use all the edges that we had originally removed from G to get to G prime. So then we have reconstructed our Eulerian circuit for G. And since we have gone from, so we've proved it for the base case of of one vertex, and now we're saying that if we assume that it is our statement is true for everything with less than n vertices, we can prove that it's true for n. So that's kind of the idea of induction. You're basically saying, okay, well, we proved it for one vertex. We can now prove it for 2, for 3, for 4, and so on. And this proves it for all numbers of vertices. Yeah, any questions about the section that we just finished?
That's 2 point again for the.
This one? All right, let me know if there's any specific questions. All right. So now we're gonna go over some basics of quantum computing, by which I mean I will give you the bare minimum you need for this presentation. But yeah, first motivation. I obviously believe we should add the word quantum in front of everything, because I think it's cool. So one of the reasons why quantum computing is cool is that if for some reason P equals NP, which it definitely doesn't, but let's say it did, classical cryptography would break, but quantum cryptography may or may not break. Come to Sig Quantum tomorrow to find out. Anyways, the reason that quantum algorithms can do things that classical algorithms can't is that we can use entanglement and superposition to store and manipulate data and explore multiple paths like simultaneously in ways that classical computers cannot. So as such, we can theoretically get much faster runtimes for algorithms that require certain kinds of computation. So I'm going to give you a bunch of words that will not make sense until the next slide, but a quantum algorithm is going to be represented by a quantum circuit that acts on some amount of input qubits. And then you're going to have a bunch of quantum gates that are going to transform the qubits. And then at the end, you're going to take a measurement on some or all of the qubits to get your results. This is what such a circuit looks like. You don't have to understand what's going on here. This is actually the quantum Fourier transform. I don't even know how it works, to be entirely honest, but all right. So there were a lot of scary words on that last slide. That is just physicists trying to be scary. A qubit is literally just a vector. So when we're working with the standard basis, which is what you'll usually be doing, we're going to have our cat 0, which is going to just be our unit vector 1, 0, and then cat 1, which is just going to be 0, 1. And so any qubit, which we're going to say has to be a unit vector, can be represented as a linear combination of these two vectors above. So there's a bunch of different forms for it, but the important part is that alpha squared plus beta squared, or the magnitude of alpha squared plus the magnitude of beta squared has to be equal to 1. And the reason for this is because, well, 1, it has to be a unit vector, and also when we then measure these qubits in the standard basis, the qubit is going to collapse into either the 0 state or the 1 state, and the probabilities are going to be alpha squared and beta squared respectively. So once again, that should be magnitude of alpha and magnitude of beta, because alpha and beta are complex numbers. Yes.
Why the probabilities would be alpha squared, beta squared, and not alpha and beta?
The calculation for the probability involves taking a dot product somewhere. Also because alpha and beta don't add to 1. All right, so what is a gate? It's just a matrix. So when it acts on your qubits, it's just multiplying a vector by a matrix, essentially. Most gates that you will encounter will be unitary, and they'll definitely be unitary. Many of them will be Hermitian. Unitary just means that if you multiply the matrix by its by the conjugate of its transpose, then you're going to get the identity matrix. Do you guys know what the dagger symbol means? Okay. So basically, it's just going to be, so say you start with like 1 plus I, 2 minus I, 3, and 4. What you're going to do is you're going to take the transpose, and so that just means kind of like flipping it diagonally. And then you're going to take the conjugate of each value, which is, so you're going to get 1 minus I, 3, 2 plus I, and 4. Can people see this? All right. Yeah, so basically you're just taking the transpose and then the conjugate of each value. Yeah, and Hermitian matrices are ones that are equal to the conjugate of its transpose. So this is obviously not Hermitian, because these are not equal. So essentially, for the purposes of today, and for unless you decide to venture further into quantum computing, quantum algorithms are largely just matrices being multiplied to input vectors in ways that can compute many values simultaneously. So yeah, don't let the physicists scare you. I have this meme here that I wanted to include. All right. Questions on this section? All right. So now we're going to go through like some stuff about quantum algorithms. So you don't really have to know that many details of quantum computing to understand some things about quantum algorithms. Most quantum algorithms, specifically for graph theory problems, do most of the work by applying the same few like simpler quantum algorithms. So as long as you know what those algorithms like return and like what their runtime is, you don't really have to know the implementation details. You can just like black box them away. So, but we do want some notions of like runtime and complexity. So we're going to say the quantum query complexity of a graph algorithm is going to be the number of queries it makes to the adjacency matrix or list representing the graph. So basically, how many times are you going to look up something in your matrix or list? Whereas the quantum time complexity is going to be the number of basic quantum operations it makes. So one important algorithm that most more complex quantum algorithms will use is going to be Grover's algorithm. The idea of Grover's algorithm is that we're going to have some function over n possible inputs, and the function will always return either 0 or 1, but importantly, it can only return 1 for at most one possible input. And then what we want to do is find this x if it exists. So Grover's algorithm can do this in O of squared of n evaluations of f, which beats the classical O of n evaluations. And that is going to be the kind of the key of why some of these algorithms will run faster with quantum methods rather than classical ones, because we can just reference Grover's algorithm. So this is what Grover's algorithm looks like. It would take a while to explain all the details of it, and if you would like to learn more, I can gladly explain things after Sigma is over. The point, what I want to point to is the U omega there. That's basically where we're calling. That is where we're actually going to be calling f of x and evaluating it. All right. So also important note about quantum algorithms. They are in some sense probabilistic, so they're not always going to be correct. They're going to output an incorrect answer with a probability like p, for example. So if we want to get the probability of an incorrect answer down to epsilon, we need to repeat. We're going to repeat the algorithm r times in order to ensure that p to the r is less than or equal to epsilon, which results through some math. Basically, we can make the probability of an incorrect answer less than 1 over n by repeating each quantum subroutine O of log n times. Yeah. So what this means, if we have a quantum algorithm with O of f of n quantum query complexity, it will typically have O of f of n log n quantum time complexity, because we're going to need to repeat that routine log n times. For Grover's algorithm, due to some weird stuff, we actually need an extra logarithmic factor most of the time, so it's going to have squared of n log squared n quantum time complexity. Okay, I forgot to add a question slide for that section, but yes.
On your previous slide, where exactly does that error come from? Is it just the real world implications of quantum computers not being perfect?
No, that adds much more additional error. Basically, because when you measure a qubit, right, there's always it's going to give you this answer with the probability of this and this answer with probability of that, and even if you amplify it enough, it's still going to have some probability of just being incorrect. It's just physics stuff. Yeah. Yes.
Can you briefly explain how the algorithm reduce the complexity? Can you explain how quantum algorithms just reduce the complexity?
So, well, okay, we'll go back to Grover's. Here, what we're doing is we're solving this quantum search problem by referencing, only having to reference f O squared of n times rather than O of n times, which means that we are solving the problem significantly faster. And a lot of quantum algorithms will reference Grover's algorithm as well as other more simple algorithms. And we can leverage that to just end up getting much faster runtimes. Does that kind of make sense?
How does it reduce the complexity? The idea.
Like the idea behind Grover's search.
Yeah, behind Grover's search.
That could be a whole presentation. I mean, you're basically you're applying this huge operator to a bunch of qubits at once, but you only have to call f of x once when you do that. So you're basically doing a lot of evaluations on a lot of different qubits with significantly less overhead than you would for in classical. I'm like trying to figure out how to explain this without,
Can I give one liner?
yeah, go for it.
Visualization, so imagine it like you have a huge database, right? And out of this, you have n values. All of them are zero, but one of them is one, and you're trying to find the one. So imagine them in a plane, and the zeros have a short height and the one has a long height. So what this operator is doing, it's putting the reflection, like it's putting another plane at one point, and you reflect it along the operator. So when you reflect it, the zeros get reflected by a short height, like after the reflection, the zeros still have a short height on the other direction, but the one's height gets amplified. And when you do it again, the one's height gets amplified more. And you keep doing it until the one's height is so much more amplified that you don't notice the zeros and you find the one. So that's the basic visualization of this. It's like in a plane, you are reflecting it along this operator so many times that the one gets amplified and the rest are small. Like that's the basic idea. If you want to understand more, I'm pretty sure Sasha would be willing to go through the math of it after the.
Thank you.
Yes, all right, that's actually a very good explanation. Does that? Oh, okay. All right, so where were we? We were here. So now we're going to talk about how quantum algorithms can make the Eulerian circuit problem faster. Now, first notably, the idea, right, is you're basically trying to find, or you're basically trying to determine if the degrees of all your vertices are even, or if there's at least one odd degree. If you were to do this with classical computers in the adjacency matrix one, it would take O of n squared time because you would actually have to go through and add up every column. Here, because you are given the degrees, it would instead take O of n time with the adjacency list, because you could just check each of the degrees. But we can get even faster with quantum algorithms. With the adjacency list model that we'll start with, as I noted, the degree of every vertex is given. All we have to do is search the list of degrees for an odd number using a simple quantum search that will be based off of Grover's algorithm. And if we find an odd number, it's not Eulerian, otherwise it is. So we basically did most of the work for this in the previous slides. There's really not actually that much you have to do to make this algorithm work. So notably, this quantum search will require O squared of n queries to the list of degrees. So it's going to have O squared of n quantum query complexity. Because we used Grover's algorithm, we're going to have that extra log factor. So we're going to have O squared of n log squared n quantum time complexity, which notably is less than O of n. Yeah, and then we're going to have the adjacency matrix model. Things will work quite similarly, but this time we don't know the degrees right away. So through a combination of Grover's algorithm with a classical algorithm, we can compute the parity of each column, meaning which we can determine if each column, if the sum of each column is even or odd, which is what we want to know in terms of the degrees. The actual details of this are kind of very hard to explain, but yeah. So if we find an odd number, once again, it's not Eulerian, otherwise it is. So the complexity here will be O of n to the 1.5, because you have the square root of n and then times n. And so it will have n to the 1.5 times log squared n quantum time complexity, which is less than O of n squared. All right, that's actually all I have. So before we get to the brain teaser, questions?
So how would you implement this?
Yeah, okay. So
Yeah.
Once in the far future, if we have quantum computers actually working, wait, are you asking how you would implement quantum computer or just the algorithm itself?
No, suppose you had a quantum computer, how would you implement on, yeah.
I mean, you would figure out the combination of gates you need, and you just code it up.
Is there specific language that you use?
Yeah, there's a few different languages that have been designed to work with quantum computers, including Qiskit, which, by the way, we will be hosting Qiskit Fall Fest here shortly. So
If you want to learn the language,
Yes,
run with the Fall Fest
yeah.
plugin, just a random plugin.
But yeah, there's also a few other languages. There's QASM. which I personally don't like, but that's, yeah.
So is like the limit right now, like, we don't have enough, we can't sustain enough qubits, or like, what's like?
That is, yeah, so in terms of the limits of quantum computing, it's kind of outside the scope of Sigma, but, yeah, there's not enough qubits, the qubits aren't stable enough either. Error correcting needs to be like sped up, and yeah, there's a lot. Yes.
Can you please explain once more why we have that login in time?
Yes, so the reason we add login is because we're going to need to repeat each quantum subroutine login times in order to reduce the error down to like a manageable amount.
So, please correct me if I'm wrong, but I always thought that that amount that we need to repeat is something constant, but we have that login because the Hadamard gate takes like login time to implement.
I don't know about that, that's.
Yeah, because I had the same question because I was dealing with something like this, and then in some papers I read like a square root of n login, and some of them just gave the square root of n. And then I searched, and in one of, I think it was Shor's paper, that he explained that this is because of Hadamard.
What Shor's paper?
I can share it with
Okay.
you.
Yeah, I'm not entirely sure what that would be.
This one, what Oxford login reason was quantum algorithms also can give you the wrong, like, you can give you the right answer probably here.
Yes.
In order for you, so that you have to run the experiment multiple times, so that whenever you get better, the probability of getting wrong is still decreases. So probability P times the factor R basically, sorry, not times, 2 raised to the power R must be less than the, like, the error, which we get it.
Yeah, I always thought that R is something constant. I didn't know it's login. I'm confused because I'm still dealing with this. I want to know if it's for that R or is for Hadamard.
So in this case, is the login the runtime of a particular repetition code or error correcting code used? Or
No, it's just because the person who actually wrote about this in his paper, just was like, we're gonna run every subroutine login time so that we reduce the error.
yeah, so
So-
it's the time of the error correcting code.
That's what we, yeah,
Just repetition, right?
yeah, so I don't think there's anything like that deep behind it other than.
So I think it can just vary because different papers or different subroutines you would have seen would have used different kinds of error correction or run the error correcting code a different number of times.
Because some papers will just say,
This one particularly is using it login time.
some papers will just say, oh, we have O squared of n runtime, but like with a probability of whatever, of getting an error. And others will be like, no, we're gonna repeat this because we don't like error. So that might be the. Alright, any other questions? Yes.
Oh, what is
N is the number of vertices of the graph. Alright. Alright, it's brain teaser time. I have no idea what this brain teaser is, but I didn't put it in, but. Well, should I read it?
It's pretty good, it's a pretty good one.
Well, I guess I'll read it. 13 apples, 15 bananas, and 17 cherries are put in a hat. Inside the hat, if two fruits of different type collide, they both get converted into the third type. For example, one apple and one banana can collide to form 2 cherries. Can a sequence of collisions lead to all 45 fruits having just one type? Huh. Okay. All right. Well, that's bibliography. Yeah. All right. Yeah.
Is what the club is going to think is people, members giving meetings, members like us, and anyone else. So anyone who's interested in giving a meeting, you don't need to have any prior knowledge. It's something that you can learn about over the course of how long and learn about the topic you're interested in. and hopefully present about it. It's a great way to gain experience and presenting and hopefully practically that they were talking about and about. So, you know, like there's only so many of those avenues we can't give the whole meeting the semester, and so we need anyone who comes, anyone who wants to do the meeting, just feel free to reach out to us on this board or if it's something you want to present on, or you just want to present on something that you only want to present on, that's perfect.
There's no test, this is just to expose you to stuff and find something interesting out of it.
And
Yeah.
we can help you with your presentation too, if you want.
Yeah.
Or you can present with someone else.
We have a template, it's really nice. Yeah.
Yeah, like you said, there's no like requirement or anything. It's something that you should like you got it.
Also 45 cherries are possible.
Okay.
Oh, they are. Well, I'll be posted.
Yeah. I'll try to get it sooner than the last one. Yeah, probably once the report.
Everyone?
Yeah, thank you, thanks.
I don't want this,